Uh, Good evening, everyone. We will start a new example, which is basically a linear elastic and elastoplastic analysis of steel sheets with a circular and square holes using ABAQUS. In this example, we are going to analyze using ABAQUS a rectangular sheet. A thickness of the sheet is 4 millimeter. The elastic modulus is 210 gigapascal, Poisson ratio is 0.25, yield stress is 450 megapascal. As you can see from the figure here that the sheet has two rectangular holes, square holes, and one circular hole. Each of the square holes, dimension of each of the square holes are 40 by 40, and the circle is 40 millimeter as a radius. Now, what you're supposed to do is, you need to, for two case studies, you need to model this model. For case study 1, as you applied a prescribed displacement, which is 2 millimeter at this edge here. So you apply 2 millimeter at that edge, goes up. In the case study 2, that you apply now not prescribed displacement, you need to apply a uniform distributed load over the edge here, and the distributed load goes up also. And the value of this distributed load is equal, is the same as the resultant of the reaction at the same edge computed in a case 1. Now, you must do this actually using linear elastic and elastoplastic analysis. Now, today we will start working on a case 1 where you have to apply this. After you model, you need to apply a prescribed displacement equals 2 millimeter and the top edge here and goes up, and you have to analyze it using elastic material and also plasticity included. Now let's start with the model. We open ABAQUS and we will choose standard explicit model, and you click. Before we carry on, we must assign or set up the work directory. We go to File and then Set Directory, and I'm gonna open here. I will go to D. I will go to one of the file I created, let's say in ABAQUS tutorial, and then OK. So here all files will be saved in D in a folder of ABAQUS tutorial, and say OK. Now let's start modeling. You go to part, you go into part manager, you click, you go to create, you click in a create and call it as a steel or sheet, steel sheet or sheet. It's a two planar, and since it's a two planar, I will choose a sheet, a shell as a base feature. Okay, now you say continue. Now, in order, first of all we need to create that big sheet of steel. So you go to rectangle here, create lines, rectangle 4 points, you click here and you enter the coordinates 0, 0, enter, and the other coordinate of the corner here should be 200 by 400. It's 200 by 400. So according to these coordinates here, so it's gonna be 200 comma by 400. Enter. Now in order to see the rectangle, we're gonna go and click on auto fit view. Click. Now we haven't finished yet, so what we have to do, we have to draw these square holes, and the first coordinate for the square hole is here, which is 40 40, and the second coordinate is 80 80. So let's go back. So we still have the same command here. I didn't cancel it. So again we can say 40 comma 40, enter, and you can see, and then 80 comma 80, enter. Now you create the first rectangle. Let's go back and you will see the other rectangle. The other rectangle here, what you have, the coordinate of this rectangle, if you notice, it is 400 from here to here, minus 40 minus 80. So it is 400 minus 40 and minus 80 will give you this coordinate in y direction, and the x coordinate is 40. So basically it is 40 by 280. This is the first coordinate. So it is 40 comma 280 is the first comma, so it's corner of the rectangle or the square. Now the other coordinate for the coordinate for the other corner is here, which is you add 40 in x, so it will be 80, and 40 in y we're gonna be 320. So it is 80 by 320. So again it is 80, sorry, I'm gonna write here 80 comma 320, enter. Now we finish drawing the big rectangle and the small squares as holes. Now because we finished rectangles, so we can cancel the procedure here. Cancel procedure, we click only one time. Now we must now draw this circle here, this circle in the middle. So the question is how we're gonna draw it. The center of the circle is, it seems to me on the middle of the plate, so it is 100 in x and 200 in y, so it's 100 by 200. So we'll go to create circle, the center and perimeter. So we click in the center circle, it's gonna ask you what is the center, which is, you said it is 100 comma 200. That's the center. Now if you move around here, you will notice that your circle is changing the diameter. So it can ask you what is the perimeter points. Now if you go to here, the perimeter point, which is here somewhere, it is 100 plus 40 is 140, and in the y it is still as 200. Or what you can do is you click somewhere, sorry, again, sorry, it is 140. So this for this point here, so 140, and in y it is still a 200. So 140 and 200. So again 140. So it's 140 in x and 200 in y. That you create your perimeter. Now we finish the holes. We cancel procedure in order to end up with a model. the drawing, and then we said done. Then you said done. Now when you said done, you will have your model with holes inside. Let's save the model, and you're gonna say steel sheet. What do you notice? It's gonna be saved in the folder you created already, and say OK. Now, next step, we need to define the material property. Now we are doing in case 1 for in the case of elastic material. So in the case 1 has two cases. In the case 1 we have two options, elastic and the plastic. Now we go for the option number 1, the elastic material assumed, so we don't include plasticity. Now let's go here, we go to material, you go to here material manager, you go to create steel material, and the mechanical, elasticity and elastic. The material property is based here with 210 gigapascal, which is 210 and 30 to convert it into megapascal, Newton per millimeter square, and Poisson ratio 0.25 as shown here. And saying that we are doing an elastic analysis, elastic material only now for a moment for this case, and then say OK and dismiss. After you create the model, you need to create a section. So you go to section manager, you go to create, and name it as steel section. Steel section. Steel section. Steel section. And then it is a solid, not a shell now. It's a solid at the thickness, which is 2D plane. It's a 2D plane stress and homogeneous, and then you continue. Basically, it's a 2D plane stress. It's not doing a shell because you assume it a shell if you have the load perpendicular to the sheet, but as you see here, the load is not perpendicular. The load will be in a plane of the sheet. Therefore, the modeling in terms of modeling aspect, here it is a solid model, but 2D solid model as a plane stress. Now it's a solid, homogeneous and continue, and the material is steel, and assume the thickness as we said, the thickness was 4 millimeter. And we remember we did an example on modeling a 2D stress analysis. In a 2D stress analysis, the element used is 2D plane stress, and we assume a plane stress only if you have the thickness of the model is small compared to other dimensions, and the load applied in the plane of that model is not perpendicular to the model. Now say OK. Let's go dismiss. Now we go into section manager assignment manager. So we click on the assignment manager, and then we create, and we click on the model and say done. And we keep everything as it is, which is our steel section. When you said OK, you notice the color is changed, meaning that we are correctly assigned the section into the plate. And then you go now to the next step, which is assembly. When you click on assembly, you notice the model is disappeared, but you need to bring it. So you need to go to create instance, get the independent mesh because you need to mesh it on the instance, and say OK. to make, okay, not apply. If you apply, meaning that you apply and then you cancel. Otherwise, you say okay to bring the model. Save your model, and then you go to a step in order to apply a step load. You click on a step, you have a step manager. You go and you create your step. You choose static general, go static modeling step, and then we will, since we are doing elastic analysis, therefore if you click on the incrementation, you will have only one increment size, which means the whole load will applied as the whole load will apply over that plate, or I mean the whole value of the load is not gonna be applied incrementally. Now, therefore we are not interested in number of increments or increment size, as because we are modeling an elastic analysis. And then we keep everything as it is. I said okay, and then dismiss. You go to loading. We're gonna do a boundary condition below here. It is fixed boundary condition. So you go to boundary condition manager, and then you say to create, and let's call it boundary condition or fixed boundary condition. We're gonna take a displacement rotation, and then we say continue. We're gonna click on this line over here, tick, and then you say done. Now it's a fixed boundary condition, therefore we will need to make this 0 in the y direction, x direction in the y direction, the displacement 0, and the rotation is also 0. I said okay. Now just assign the boundary condition. You go to load. Now the load here has a displacement. So in this example, it is displacement control. So basically I will apply a displacement over here, over the top edge, and this displacement goes up. This procedure called a displacement, prescribed displacement or displacement control. Here the load applied as a displacement is not applied as the load or pressure. The load applied as displacement is very good when you do a nonlinear analysis, because the displacement, as the displacement increase, the load may increase or decrease. So in displacement control, it can capture the ultimate load. Let's get a more understanding of. Let's go. I'm gonna draw something about it. So basically, assume you have, this is x-axis as the displacement and the y-axis as a load. So this is displacement, this is displacement, and here is the load. Okay, sorry. Now, if you apply a displacement, which is called displacement control, what gonna predict? So, as you apply the displacement, you will have the load could increase, as you see. As the displacement increase, the load increase. So as the displacement increase, the load increase. So we carry on. Now assume the load or the sheets or any model attain the maximum load. What's gonna happen? It could make it stable. It become as as the displacement increase, the load become constant, or the load drop down. As the displacement increase, the load drop down. Now, which means that in displacement control, as the displacement increase, the load the load value it changed could increase or become constant or decrease. So the whole behavior of a structure or your model will be captured as if you apply a displacement control. Now, if you apply now load only, not displacement, load. So let's clean it up here. So if you apply a pressure or load, as the load increase, your model will capture now displacement. As the load increase, capture displacement. So what happened here? It's gonna attain the ultimate load here and become constant, and once the load it should drop down, it cannot be dropped because in a load control you only attend the maximum load we given to you because the load is applied incrementally. As the load implied incrementally, so assume your load is, let's say you apply a load of 10 kilonewton, so it attend up till, for example, 9 kilonewton load, and therefore it cannot carry on, which represent the maximum capacity is 9 kilonewton, and therefore as you are applying a load control, it cannot predict what happened after the ultimate load. Therefore, the displacement control, it gives you the behavior after it, while the load control cannot give you the behavior of the structure after attending the maximum load. However, on the other hand, if you want to know if you apply a load and you want to apply and you want to know the behavior after, you must use arc length method. But we're not gonna use it. In this example, we will apply displacement, and the other case we will apply load and show the differences between. Now let's come back and apply displacement, and then you go here. So we're gonna apply displacement by applying boundary condition manager again, and then we're gonna create and displacement and rotation. Let's call it as prescribe displacement, prescribe displacement, and then you continue. You will click on that edge and say done. You want displacement in y direction up by 2 millimeter. That's 2, and saying okay. Okay. So that edge will apply displacement up. Okay. Now let's close it. Let's go to mesh. Let's now, in the previous lectures or previous videos, we focus on define exact number of elements. Now here I will use an automatic mesh capability in ABAQUS. We usually use the seed edge. Now we will ask ABAQUS, okay, can you use the seed part instance? So if you click it here, it will ask you the global size of the element. Assume the global size of the element approximately by 10 millimeter. So ABAQUS will divide that element into divide that model into element by approximate size by 10 millimeter. And then we said okay, and you will see that seed is generated and saying okay. Now when you go and mesh part instance and you click here and you said okay, you need to mesh it, ABAQUS will automatically generate that mesh based on the assumption of approximate mesh is 10 millimeter. Now let's go to define the type of element. You click here and you click on the plate and say done, and I will not use introduce integration, and I will use actually a plain stress, not reduce integration. And let me see in the tutorial what type of element. I just try to, because I need to be consistent with the tutorial. Mesh element I use, element use, okay, quad, triangle. Okay, yeah. Now I choose quadratic and reduce integration. That's fine. So we're gonna use this type of element. So quadratic and reduce integration. Okay. Now we're gonna use quadratic, which is and reduce integration. I will keep it as it is and say okay, not linear, quadratic, reduce integration, or okay. And done. I just want to mention about here, which is assign mesh control. Click it and let's see what is going on here. And we have a number of options, which is quad or quad dominated or tree. And I would try, I think this is not gonna be big differences between a quad dominated and a quad. I'm gonna try to click on a quad and see any differences. Said okay, just come to you here as we said, can we mesh delete the mesh? He said okay, delete the mesh and re-mesh it again. We click here and okay, it seems there's no big differences. Okay, we keep it as it is. So basically all the elements are quad elements. Then another code to job. You go and create job, you go job manager, then we create, let's call it case 1 elastic material, and said okay, continue, okay, and submit it. Let's wait the analysis to finish. If you click monitor, you can monitor what's going on. To make sure that your model is input is correct, you will see this message: analysis input file processor complete successfully, which means your input is correct. once you see the model, the job is completed, so that's fine, and you get the result. Okay, that's your model. Let's go into what you really want to get from that model. What type of result? Let's go into the last page of the model here, the last page here, and you want linear elastic result. I want your results von Mises, stresses in a y direction S22, stresses in x direction S11, a deflection in y direction U1. And you want to do it for a point 1, 2, 3, 4, 5, 6, 7. Okay. 1, 2, 3, 4, 5, 6, 7. So let's try to fill up these tables. Now, go to here. Now let's focus on von Mises. Go to here. Go to your model. If you click in the plot contour on the deformed shape, it will show you the deformed shape. Now, what do you really want? I want the stresses, which is von Mises stress here, on the corners, and the corner here, and on the circle. And then let's do that. Now, let's do that by, let's go into here to this good tool, which is query information. Query information. Click on node and prop value. It brings you into this window. Change the prop into a node because we are not finding the nodes. Now 1, 2, 3, 4. So now if you closer to this node as you want to find, and you can zoom actually out and in as we teach you by rolling your mouse. So let's zoom in, and then you close a bit. It will give you actually the stress, which is 969, which is 969.037. That's your stress here. So it's 969.307. So let's write it here. So it is 969.037. Okay, and then the next point is 2. Move a bit close, 2, which is 2108.9, 2108.9, and node number 3, which is 1370.16, 137.16, and the last one is this one, which is 2064.5, 2064.5, and the 0.5 is here. So you go zoom out to pick up and zoom in to pick up this edge, which is 1707.9 sorry, 1707.9, and then we need a circle. So in the circle I need here this point 6 and 7, these points. So let's go to 6. It seems confusing a bit. Let's click here actually on undeformed shape. Now it's a bit clearer. So kind of, okay, let's get this point here. This is a point which is 2986.87. Now 2986.87. 86.87, and the last one is here, which is 1230.44. 1.1230.44. The same procedure we can now find for S11. Find it now for S22 and S33 is the same thing. So what S11, which is stresses in y direction. So S11, you go to stress, and S1, sorry, this is S11, yeah, S22, sorry. So S22, which is a stress in y direction, and again you repeat the same procedure. You will see here, so this value, which is 850.6, C's value is 1757.01. The third value is 1014.5. Here is 1611.15. I'm writing this down, and then I go to this corner here, which is 1419.3, and now I need to circle, and this seems a bit confusing. Circle, so you click on antiform shape, and then you go to here. It's 3027.6, and the last one is somewhere here between, which is -5. It seems -60. Okay, now let's go back to S22. So this is S22 what we found out. This is S22, yes, yeah. So S22 is basically 80.6, 1757.01, 1014.5, 1611.15, 1419.3, 3027.6, and -60. Now S11, we go to S11, go here. This is 22, let's go to S11, we change it to S11 with the same. So we go here, these corners. Why I care about these corners? Because the most significant stresses is these corners. Because in these corners, the stresses is a very big. I will show you. For example, go back to Mises. Go back to Mises. Or Mises. Click here. Click here. It's about 969. You click here, which is about 2000. Click a bit away from 2000. It's changed. From here, the maximum is 2100, while here it's 1300. It's much less. It's simply because the stress here concentrated more around these edges. Also, if you notice here is 1000, while it's here about 2000. So when you have rectangular section, the stress distribution will be more, while the circular is the stress will be not concentrated more. Now we're back to S11. So now it is minus 38.2. You click, go here. It is 439.6. You go here. It is minus 427.84, and the last one here, it's 818.6. Okay. Now you go to your last one here, and you click here, and then you have a 685.64, and the circle. Let's undeform it, and then we can move around here at 4.3, and here, which is minus 1259.3. Negative means it's a compression, positive is a tension. Okay, let's go to this here. So S11 is minus 38.2 and 439.6 minus 427.84 and then 1 so and 818.6 685.64 84.3 and minus 1259.3. Oh, that seems high. Yeah, okay. Okay, now lastly U2 also. Again, you go to a model. So this is stresses. Now let's go to the formation U and U2 in a y direction. So let's go. It seems he's a maximum. So you click here, you will have 1.8 second node, 1.7, about 1.7, it is 1.35, and the last here 1.56. And then we go to the point here, the nodes here, which is I want it is 0.35, and that's for the circle and deformed shape here, and you can rove around here, or sorry, closer, it's 1.04, and the top here is 1.56. Let's go here, and then you can write 1.8, then 1.7, 1.35, 1.56, 0.35, and 1.04, 1.56. Okay. Now you've got these results. Of course, these are in megapascal stresses and displacement in millimeter. Now I would like to show you something also which has a good capability in ABAQUS. Now this is deformation. Let's go to the stresses. Let's say stress S, and the stress is S11, let's say, which is in X direction. If you go below here, this is plot samples or samples on deformed shape, and if you click it here, what do you see actually? It is a direction of the stresses. That's interesting here. So you can know the direction of the stresses on different point. Let's go close here, and this node will have a direction here. It seems it's not written drawing here, but as you see is if the arrows goes inside mean there's a compression, if the arrows goes outside there's a tension. Let's go one of these arrows. At each node there's a value, and the length of the arrow represent how much a value. Go for example to S22. You notice that the arrows shows vertically, which is S22. If you look closer, and this go a bit here, click here and then get undeformed shape. If you come closer, you will see actually you will see for each integration point, basically is not at each integration point the value and the direction. So it can give you actually a direction. If you go for example the principal stress, also this maximum principal stress is give you the direction of maximum principal stress, which is quite interesting. If you see the maximum principal stress direction, this give you not only values and the direction of principal maximum stress. As you notice around here, around the square is the maximum principal stress. It goes around it and it change the direction, something like this, which is interesting to see what is going on, the maximum principal stress. And if you notice the maximum principal stress around the circle is rotate around the circle. the direction, which is interesting. And if you go to minimum principal stress, and you will see the minimum principal stress somehow different behavior. So it's a shape. So it is quite interesting to know how the stresses direction, how the direction of stresses over here. So let's cancel that by going again to the contour plot. So I give you on the contour. Even displacement, if you want to see the displacement, you go to displacement as a magnitude, and then if you click again here, the plot simple and deformed shape, you will see the, sorry, I think it's a mistake. You have to go here again when you click this, the simple shape, and then you go to U, and then you go to resultant, for example, and you will see how is the deformed shape in each integration point, or this, sorry, the direction of the displacement at each integration point. Okay, now click here again. The second question is result, the result for the reaction force at the top edge. Now we need to find out the result, which is a reaction force at the top edge in kilonewton. We're gonna write it down here, and yeah, okay, we've got, yeah. Now that is the reaction in kilonewton. So what we have to do, how to find out the reaction at the top edge. Okay, this procedure could be for the top or the bottom edge, it doesn't matter. Now let's do the top edge. What is the reaction at top edge? It means you apply a load, displacement, but what is the load generated? Sorry, in order to do that, you go into RF, which is reaction forces, and you choose not the magnitude, you choose in Y direction only, which is RF2. Now you need to focus. Let's close this here. I'll close this. Let's focus. This is very important how to do that, to find the reaction. If you take a query information, you take node, prop value, what do you, and then you took nodes. What do you notice? You have at each node there's a value of the reaction. Now, do we need to take this value and record it, and take this value and record it, and take this value and record it? Each of these values, do you need to record them and then sum up all of these together? That's a difficult task. There is another way actually given in ABAQUS, that you can define the whole nodes at one go, the value of these nodes at one go, and ask ABAQUS to sum these all together. Let's do that. Close this. Let's close this. So RF2, you go to tools, and then XY data, and then manager, and then go create, then go to ODB file output, and then continue. Now it chooses a position, not integration point, as a unique nodal. So I need a unique nodal here, and it chooses reaction forces as RF2 in the Y direction, reaction in the Y direction, as I apply the load in the Y direction. And then you go to element nodes and edit selection. Yes, edit selection. So we're gonna ask you select the node in a viewport. Move this a little bit back, and then zoom it a little bit, and then create a window in order only to choose only the top node, not to try to exceed. In this way you choose all nodes. If you, for example, exceed like this, you choose a lot of nodes. We don't need these nodes. I only need this top node. That's the top nodes, and say done. So you selected 41 nodes, and then save and said okay. Now, if you click any of these, will give you the value at each of this node 27, this reaction, and the node to 121. This is a reaction. I don't need to click all of these 41 times and jump them. So I will sum this all together. So go to create, you go to operate on XY data, and then you said continue. You go into the screen here and you put your cursor here and you go to sum. If you go here, you find sum somewhere here. You go sum, is it sum here? Yeah, that's a sum. You click sum. Now inside this bracket, you need to click, you take all this data into here. So how you do that? You click from the start and you keep clicking and you drag down your mouse all the way down until you select all of these. If you go down, you will find, if you drop down this, you will find all this selected, and then you say add to expression. You add it into expression. Now what's happening is this all will be summed up, will be summed, and then at the end will give you in a Newton. Now as if the question is I want it in kilonewton, so simply you could at the end of the expression or the end of the operation, you put divided by 1000, so the whole summation will be given in kilonewton, and then save as, you keep it, and then OK. What you notice, you will notice that the final here are the sum, and you double click and it will just give you the value of the summation, which is 625.26. Copy this and bring it into here. So in this way we finish the first part of the tutorial by giving a linear elastic analysis for prescribed displacement. It's time now, it's about 1 hour. So my advice to you now to repeat the whole process, and next week we will do elastoplastic analysis, or another video we will do elastoplastic analysis with refined and unrefined displacement. After that we will finish this. Thank you very much for your attention. I'll see you later.